Welcome back to the Deep Dive. Today, we're going deep, really deep, into the silicon.
Yeah.
The actual physical hardware that powers modern artificial intelligence.
It feels like for the last 5 years, the whole conversation around AI has been about algorithms, bigger models, new transformer architectures, clever prompting.
Right, it's all been about the code. But the consensus now, among all the experts we've looked at, is that the algorithms have hit a wall. Or rather, they're being bottlenecked by the hardware.
That's such a great way to put it. If you think of AI as a rocket, the code is the guidance system, sure, but the chips are the fuel. And right now, we are in the middle of this incredibly high-stakes technological war, the AI chip wars.
Our deep dive today is going to focus on the central conflict, the real clash of titans, Google's very specialized ASIC, the Ironwood TPU v7, versus NVIDIA's reigning champion, the Blackwell GPU platform.
It's like a fascinating battle.
So our mission today is to really take you inside this foundational conflict. And you might be asking, why should I care?
And the answer is because these little pieces of silicon, they determine everything.
Everything. The speed, the cost, the feasibility of every single AI application you're going to use for the next decade.
From the LLM you're talking to on your phone to, the emergence of genuinely autonomous AI agents, it all comes back to the chip.
So we're going to give you the whole historical roadmap. We're going to look at the architectural blueprints of these two Goliaths, and then we're going to try and peer into the future, looking all the way out to 2035.
And the sources we've compiled, we're talking everything from dense architectural white papers to market forecasts. They all point to one definitive trend. The main battlefield isn't about raw speed anymore. It's not just about maximizing FLPS.
That ship has sailed.
Completely. The new fight, the one that really matters, is all about energy efficiency and specialization. It's for what we're calling the age of inference.
And that's the pivot, isn't it? That's the crucial thing to understand. Training a model is still hugely expensive. It's this massive upfront investment. But you only do it once, or maybe a few times.
Right. But inference, that's the day-to-day. Once that model is trained, it's on, 2047. It's handling billions of requests. It's reasoning, summarizing, creating, planning.
Constantly. And that's where, 80–90% of the total cost and energy consumption actually lives?
Exactly. So making that process cheaper, more efficient, that is the #1 strategic imperative for both Google with Ironwood and NVIDIA with Blackwell.
Okay, so to really get a handle on how sophisticated these new chips are, we have to rewind a bit. We need to see how we got here, how we moved from these general do-everything computers to this new era of extreme specialization.
Let's do it. It's a great story.
So our story really begins, like most computing stories, with the CPU, the central processing unit. For decades, it was all about Intel and AMD. That was a game.
The CPU was the undisputed king, the workhorse. It was designed from the ground up for sequential processing.
What does that mean exactly? This is sequential.
It means doing one thing at a time, but doing it very, very fast. Think about it. Running your operating system, managing your files, loading a web page. These are complex tasks, but they happen in a sequence. The CPU's brilliance was its versatility and its ability to switch between these different tasks incredibly quickly.
So it's a master of all trades. It excels at tasks where you need that low latency single-thread performance.
Precisely. But then, in the early 2000s, this old idea of large neural networks started coming back into fashion. And it became obvious almost immediately that the CPU was just spectacularly bad at it.
So why the mismatch? Why was it so ill-suited for AI?
It all comes down to the math, the fundamental mathematics of deep learning. At their core, neural networks are just a series of massive, repetitive, linear algebra calculations.
Like the famous matrix multiplication.
Exactly. They're often called GEM for general matrix multiplication. The thing is, you're not asking the computer to do one complex thing. You're asking it to do thousands or even millions of identical, simple calculations all at the same time, in parallel.
And the CPU architecture, with its handful of very powerful, very complex cores, was just never built for that kind of massive parallelism. It's like trying to plow 1,000 fields at once with a single, highly engineered Swiss Army knife.
That's a perfect analogy. You've got the best tool for one job, but you need to do 10,000 jobs simultaneously. And we have these anecdotes from that era, the sources are full of them, that really illustrate the pain.
I can imagine.
Researchers trying to train what we'd now consider tiny models on pure CPU clusters. It was agonizing. We're talking weeks, sometimes months of compute time.
For just one experiment.
For one experiment. And the energy consumption was just astronomical. It made any kind of large-scale AI research practically impossible unless you were at a handful of very well-funded university labs or, a government institution. The computational hunger of AI just completely outran what the general-purpose CPU could provide.
Okay, so necessity becomes the mother of invention. The solution to this parallel processing problem had to come from somewhere else, and it came from a completely different corner of computing: video games.
This is the first great acceleration, the rise of the GPU.
The graphics processing unit, pioneered by companies like NVIDIA with their GeForce line, starting back in 1999.
That's right. And it was born out of a very specific need to render complex, three-dimensional worlds in real time for gamers. I mean, to make a realistic image on a screen, you have to calculate the color, the shading, the position of millions of pixels all at once.
You have to do it over and over again 60 times a second.
Exactly. So instead of having a few really complex, powerful cores like a CPU, the GPU evolved to have thousands of smaller, simpler cores. Each one was designed to do just one thing really well: those repetitive parallel shading calculations.
And that architecture, designed for making video games look pretty, turned out to be this perfect, almost accidental fit for the matrix math in AI.
It was a perfect match, but it wasn't automatic. The transition from graphics to general compute really was solidified by one single pivotal moment. All our sources point to 2006.
And the launch of NVIDIA's CUDA platform.
CUDA. It was a software layer, a programming model that let researchers and scientists directly access and program those thousands of GPU cores for general-purpose computation.
So it's like they handed over the keys to the engine.
They did. For the first time, it wasn't just for graphics anymore. They called it GPGPU, general-purpose computing on GPUs. And overnight, the entire landscape of scientific computing changed.
And you saw the impact almost immediately, right? With breakthroughs like AlexNet in 2012.
AlexNet is the classic example. It was a computer vision model that basically kicked off the modern deep learning era. And it was famously trained on just two powerful NVIDIA GPUs.
And training times for models that used to take a month on CPUs
dropped to a matter of days. That change wasn't just an improvement, it changed the very feasibility of research. It allowed for rapid experimentation, which fueled the entire deep learning revolution of the 2010s.
And the strengths of the GPU from back then are still fundamental today. You've got incredible throughput, flexibility with different data types like FP32 and FP16, which are crucial for research.
And massive memory bandwidth to feed all those cores. But the real strength, and we're going to come back to this again and again, is the CUDA software ecosystem.
The moat.
It's a massive, deep moat. For a decade, if you were doing deep learning, you were speaking CUDA. It became the default language, the industry standard, and that gave NVIDIA a huge, huge advantage.
Okay, so the GPU's dominance was clear. But as AI models got even bigger and the scale of operations grew, one company realized that even a general-purpose processor optimized for parallel tasks might not be optimized enough for their specific hyperscale needs.
And that company was Google.
And their answer was the Tensor Processing Unit, or TPU.
This brings us to the next stage of evolution, the ASIC, the application-specific integrated circuit.
This is the definition of specialization, right?
Absolutely. Unlike the GPU, which is a generalist that was adapted for AI, the TPU is built from the ground up for one thing and one thing only: the tensor math that defines neural networks. It makes a huge strategic sacrifice.
It gives up that versatility of the GPU.
For pure, raw, purpose-built efficiency.
And the origin story of the first TPU, the V1, which came out in 2016, was all about internal necessity, wasn't it?
Purely. Google's own internal workloads, things like search ranking, language translation, recommending videos on YouTube, were running at such an enormous scale that using commercially available GPUs was just becoming too expensive and too power hungry.
They were burning too much money and too much electricity.
To put it mildly, they needed something radically different. And they found that efficiency through this extreme specialization. The absolute core of the TPU is a piece of architecture called the systolic array.
Okay, systolic array. That sounds complicated. Can you break that down for us? What's a good mental model for that?
Imagine a perfectly drilled army of processors. Data doesn't get fetched, calculated, and then put back into memory. Instead, it marches in lockstep through this grid of arithmetic units.
So it's like an assembly line.
A computational assembly line. Data streams through, getting processed at each step. This drastically, and I mean drastically, reduces the time and energy that's normally wasted just moving data around the chip.
And that concept minimizing data movement, that's the real key to ASIC efficiency, isn't it?
It is the single most important factor. Less data movement means less energy consumed and higher throughput. It's that simple. On top of that, the early TPUs focused heavily on lower precision data formats.
Things like bfloat 16 and INT8.
Right. For production, high-volume inference, you don't always need the super high precision you use for training. Using lower precision is perfectly acceptable, but it hugely cuts down on the computational complexity and the memory needed.
And crucially, all of this hardware was designed to be tightly integrated with Google's own software stack.
TensorFlow, JAX, and especially XLA, their compiler, it was a full-stack, vertically integrated solution.
So if we just look back at the trajectory that all our sources confirm, it's crystal clear. We went from CPUs, the general work,
Or GPUs, a parallel generalist.
and now to these AI-specific ASICs, like TPUs, but also AWS's Trainium, Microsoft's Maya. Specialization is the only path forward for scaling modern AI.
It's the only way to manage the cost and the power.
Which brings us directly to Google's latest architecture, Ironwood, the TPU v7. The sources we've seen are really clear that this isn't just a faster chip. It represents a profound strategic pivot by Google.
It really does. Ironwood is engineered from the ground up for this next stage of AI, what we call the age of inference. We're past the point of just training models and being impressed by them.
Right. We're in the era of deployment.
We're in the era of AI agents that have to run continuously, that have to reason and search and act in real time for billions of people. And the cost structure of that kind of operation demands hyper-efficiency.
And we noted that critical data point earlier. AI training is growing, but is growing linearly. Inference, on the other hand, is growing exponentially.
It's the hockey stick graph. Inference is now the dominant cost and the dominant energy consumer for AI globally. So if Google can win the inference efficiency race, they effectively win the economic race for their entire cloud platform.
That's a huge strategic advantage.
It's everything. And Ironwood is the culmination of a decade of refinement. You can trace the lineage. TPU v2 was for the cloud. V4 introduced those amazing optical interconnects. V60 Trillium started to really focus on inference.
And Ironwood is the peak of that. The focus is almost exclusively on inference speed, power reduction, and app, and this is key, serving massive context windows.
That last point is so important. Because if you have a model that can use 1 million tokens of context, an entire book, let's say, that memory retrieval and processing has to happen every single time a user hits send. It's a massive memory challenge.
Okay, let's get into the blueprints then. Let's look at the architecture, because this is where that specialization really becomes concrete. Ironwood is Google's first dual chiplet TPU.
Which is a remarkable piece of engineering. The chiplet approach is a huge trend across the entire semiconductor industry, but it's especially beneficial for a company like Google.
Why is that? Why is splitting the processor into two smaller pieces better than making one giant one?
You get two massive engineering wins. The first one is yield. It is exponentially harder to manufacture one giant, perfect chip than it is to manufacture two slightly smaller ones without any defects.
So you get fewer duds coming off the production.
Way fewer. If one of the two dies has a flaw, you only have to discard half the material, not the whole thing. It massively improves reliability and brings down cost. The second win is scalability.
How so?
They connect these two compute dies using a proprietary high-speed die-to-die interconnect. And our sources say this link is 6 times faster than what you'd get with a standard networking protocol. So it lets them build a much larger, more powerful processor that acts like a single unit, all while making it easier and cheaper to manufacture.
So beyond just the physical structure, the sources also detail this really innovative hybrid compute design. It has 2 different types of cores, which seems perfectly tailored for modern LLMs.
Especially for the really efficient architectures we're seeing now, like mixture of experts or MOE.
We should probably explain MOE here. It's a term people hear a lot now.
Definitely. So think of a traditional monolithic LLM as asking one single brilliant expert to answer every question you have, no matter the topic. That one expert has to wake up and process the entire request every single time.
Which is computationally very expensive.
Very. A mixture of experts model and MOE is more like a specialized consulting firm. When you ask a question about, say, physics, a router inside the model only wakes up the physics expert submodel. If you ask about poetry, it wakes up the poetry expert.
Now, because you're only activating a fraction of the total model for any given task, you save a huge amount of energy and time.
A massive amount. And Ironwood is built to capitalize on this. Its hybrid design features two standard tensor cores, which are for the dense calculations, like the main attention layers in a transformer,
The heavy lifting.
the heavy lifting. But it also includes four of their fourth-generation sparse cores. And these are engineered specifically to handle those sparse workloads. The MOE routing, the large embedding tables you see in recommendation engines, all the places where only a few calculations are active at any one time.
So it's a hardware design that mirrors the algorithmic efficiency of the software. Minimal wasted energy on pathways that aren't being used.
That's it, exactly. And the core matrix engine itself, that systolic array we talked about, it also made a huge leap. It's moved to these massive 256 by 256 tiles, and they're fabricated on TSMC's advanced N5 process.
And a bigger tile just means you can process more data at once.
A larger systolic array tile means you can handle a bigger slice of the matrix multiplication simultaneously in a single clock cycle. This dramatically reduces the latency, the time it takes to generate the next word in an LLM's response. It boosts throughput, it boosts speed. It is a direct hardware optimization for the primary function of these frontier models.
But all of that incredible processing power is useless if you can't feed it with data fast enough. And the memory revolution in Ironwood seems like it was designed specifically to handle those giant million-token context windows we were talking about.
It was. Memory capacity and memory bandwidth are, without a doubt, the #1 bottleneck for large language models today, full stop.
And Ironwood's answer to that.
The answer is staggering. 192 gigabytes of HBM3E memory, that's the fastest stuff available, per chip. And that's supported by 7.37 terabytes per second of memory bandwidth.
Wow. Can you put that into perspective for us?
To put that into perspective for you, that is 6 times the memory capacity of the previous generation, Trillium. 6 times.
Why such a huge jump?
Because serving those 1 million plus token context windows, allowing the AI to ingest an entire legal case file or years of a company's financial records, requires holding all of that data instantly accessible to the processor. You can't have it sitting on slower storage. Ironwood was built from the ground up to remove that memory capacity bottleneck entirely.
So the Ironwood chip itself is clearly revolutionary. But the real showpiece, the thing that makes it all work, is the hyperscale environment it lives in. The Google Cloud Pod architecture.
This is where it gets almost mind-boggling. We are talking about pods of 9,216 interconnected Ironwood chips.
9,000, all working together in a 3D torus topology. That scale it's almost impossible to really grasp.
It's not just that it's big, it's architecturally unified. The 3D torus topology means the chips are linked in 3 dimensions, like a cube lattice. This allows data to flow incredibly efficiently between any two of those almost 10,000 nodes.
So it makes the entire pod function less like a cluster of individual computers.
And more like a single, massive, distributed supercomputer.
And the secret sauce to making that distributed system actually work is the interconnection, right? Google's proprietary optical interconnect strategy, their optical circuit switches, or OCS.
Absolutely essential. These OCS provide these ultra-high-speed 9.6 terabits per second links between the chips. The optical nature means you get super low latency even over the longer distances inside a huge data center.
And crucially, the OCS allow the architecture to be dynamic.
That's the key. They can reconfigure the network on the fly. If a research team needs a cluster of 128 chips for a new training run, the OCS can instantly create that private, high-speed cluster for them. If another team needs 9,000 chips for a massive inference task for a new product launch, the system just adapts.
And what does that translate to in terms of memory?
It results in a mind-blowing 1.77 petabytes of shared memory across the entire pod.
A petabyte is 1,000 terabytes. So nearly 1,800 terabytes of memory that can be dynamically shared.
That's right. That dynamic, unified memory access is exactly why Google can credibly claim that they run their biggest frontier models, like Gemini 3, entirely on their own internal TPU stack, both for training and for serving.
Which brings us back to what you said is Ironwood's most impressive achievement: energy efficiency. This is where Google makes its financial case to its customers and to itself.
The numbers are staggering. Our analysis of the white papers indicates that Ironwood delivers twice the performance per watt compared to its predecessor, Trillium.
And compared to older generations.
It's 6 times more efficient than TPU v4. We are talking about a nearly 30-fold improvement in performance per watt over the TPU v2 architecture from just a few years ago. This isn't just an incremental improvement, it's a leap in sustainability that is truly industry-defining.
And that efficiency, it translates directly into user experience and cost, right?
Directly. Time to first token latency. That's the speed with which an LLM starts talking back to you drops by an astounding 96%. This fundamentally changes how AI agents feel. It makes them feel like real-time responders, not like you're waiting for a computer to process.
And for Google's bottom line,
For Google and for their cloud customers, serving costs fall by 30%. In a global AI market that's measured in billions and billions of dollars, a 30% cost reduction is a monumental strategic advantage.
and we can't ignore the meta-innovation here. The fact that Google used its own AI design tool, something called Alpha Chip, to optimize the physical layout and the thermal distribution of the Ironwood chip itself.
That's the feedback loop, isn't it? AI designing better hardware for AI to run on. It almost guarantees that these efficiency gains are going to continue to accelerate, potentially beyond what human engineers could even conceive of.
So Ironwood is undeniably the champion of scale, of cost optimization, and energy-efficient inference. But standing in its way is the company that basically defined this field for the last decade,
The 800-pound gorilla.
NVIDIA. And their response to this specialized threat from TPUs is the Blackwell platform. We're talking the B100, the B200, and the Grace Blackwell superchip, the GB200.
And this platform is NVIDIA's direct answer to the scaling limits that even their hugely successful predecessor, Hopper, the H100, was starting to face.
Hopper was the engine of the first wave of LLMs, right? ChatGPT was trained on H100s.
It was. But as models ballooned from tens of billions of parameters to potentially trillions, Hopper started hitting some serious bottlenecks, specifically around memory bandwidth and, most critically, interconnect throughput.
So the communication between the chips.
Exactly. If you're training a trillion-parameter model, it has to be spread across hundreds or thousands of chips. The sheer amount of data you have to constantly shuttle between all those chips becomes the limiting factor, not the compute speed of the chips themselves.
So Blackwell, which is named after the influential statistician David Blackwell, is engineered specifically for what they call exascale demands, the true AI factories.
The AI factories that will build the next generation of generative AI models. And we really have to emphasize the context of NVIDIA's market dominance here. Even with the rise of all these ASICs, our market analysis confirms that as of late 2025, NVIDIA still controls roughly 90% of the entire AI GPU market.
90%.
And the sources note they shipped over 6 million Blackwell units in the first year alone. So Blackwell isn't just another powerful chip, it is the foundational infrastructure on which the entire global AI industry is being built.
Okay, let's dissect the Blackwell architecture.
Yeah.
Just like Ironwood, it's a dual die design. But NVIDIA's execution is tailored to maximize raw power and, importantly, flexibility. They achieved what's called a reticle breaking design.
So a reticle is basically the physical mass that's used to etch the chip's design onto the silicon wafer, and it has a maximum size. You literally can't make a single chip bigger than the reticle.
So they broke that limit.
They worked around it. By using their proprietary technology, NVIDIA fused two massive dies. Each one has 104 billion transistors made on TSMC's custom 4np node, and they fused them together with this incredible 10 terabytes per second chip-to-chip interconnect.
So it essentially tricks the software into thinking it's one giant chip.
It allows the combined 208 billion transistor behemoth to function as a single unified GPU. It's a clever way to effectively double the size and power of the chip while keeping manufacturing yields high.
And the engine driving the whole thing, the generative AI revolution, is the transformer architecture. And Blackwell's core innovation is what they call their second-generation transformer engine.
This is where they address the massive computational challenge of these models head-on. The huge breakthrough here is the support for dramatically lower precision data formats. We're talking FP4, FP6, and FP8.
We talked about how lower precision helps efficiency with TPUs, but you're saying FP4 is truly transformative.
It is. By shrinking the data footprint of each number in the model's weights, FP4 essentially allows models that are twice as large to run within the same amount of physical memory.
Wait, say that again. Twice as large?
Twice as large. You can fit a model with twice the number of parameters into the same 192 gigabytes of HBM3 memory.
And what does that mean in practice? For a user, for a developer?
It means NVIDIA can deliver up to 30 times faster inference performance in optimized paths compared to Hopper without having to sacrifice the model size or accuracy that you need for these frontier models. It's a massive power and efficiency gain, all achieved through a clever way of representing the data.
The sources also detail the ultra-tensor cores, which are optimized for the most taxing parts of a transformer, the attention layers and memory-bound stages.
These cores are so crucial. The attention mechanism is where the model synthesizes information across its entire context window. It's the most computationally demanding part. By optimizing the ultra-tensor cores for this specific task, NVIDIA achieves 2 times faster attention operations compared to the previous generation.
So Blackwell's hardware is maximally tuned to the transformer algorithm.
It recognizes that the transformer is the algorithm of record for modern AI, and the silicon is built to make it run as fast as humanly possible.
And on the memory front, Blackwell has 192 gigabytes of HBM3E, which mirrors Ironwood's capacity, but they managed to eke out slightly higher raw bandwidth at about 8 terabytes per second.
Right. And again, this just highlights the new reality. Massive on-chip memory capacity is no longer a luxury. It's an absolute necessity for dealing with multi-trillion parameter models.
But the raw chip specs, as impressive as they are only half the story for NVIDIA. Their real strength lies in their ability to scale those chips into huge, flexible clusters. That's all cemented by their software ecosystem.
The interconnect is the key here, the 5th generation NVLink. The NVLink provides 1.8 terabytes per second of bidirectional bandwidth per GPU. This isn't going over a standard network. This is a high-speed, dedicated link, and it allows researchers to build these massive clusters of up to 576 GPUs that can all talk directly to each other without needing to go through a slow external CPU.
And that level of cohesion leads directly to the NVL72 rack, which is one of their key products.
The NVL72 is literally an AI factory in a box. It's a 72 GPU cluster that operates as a single massive GPU with unified memory. The reports we've seen suggest this delivers 65 times more compute capacity for reasoning-type inference compared to a similar cluster built with the older H100s. It provides the architectural glue you need to run the world's biggest models.
And for workloads that need that mix of high-speed CPU interaction and GPU power, they have the hybrid design, the Grace Blackwell Superchip, or GB200.
The GB200 is fascinating. It pairs one of their own ARM-based Grace CPUs with 2 Blackwell dies over a 900 gigabytes per second NVLink C2C interconnect. This pairing is essential for memory-intensive, low-latency tasks that need constant CPU oversight.
Like what?
Things that rely on dynamic scheduling or tasks that need to access vast external databases constantly. It provides up to 20,000 FP8 TFL OPS per superchip, giving developers maximum flexibility.
Okay, but let's step back for a second and talk about the biggest moat of all. The one factor that Ironwood, for all its brilliance, simply cannot replicate.
The CUDA ecosystem.
The CUDA ecosystem.
It's the bedrock. It's this comprehensive, mature software stack that has been built and refined for over a decade. Every major research paper, every AI framework, PyTorch, TensorFlow, JAX, every graduate student, every engineer, they are all fluent in CUDA.
So Blackwell isn't just a piece of hardware.
It's the physical manifestation of the most dominant software platform in AI history. If a rival chip comes out and is proven to be, say, 10% faster at some niche task, the vast amount of time, effort, and sunk cost required for a customer to port their entire software infrastructure away from CUDA is usually just deemed too high.
It's a massive amount of friction.
That market friction is NVIDIA's greatest strategic asset. It's an incredible defense.
Okay, so we've introduced the two champions. Now we get to the battle itself. Our sources describe this period, late in 2025, when the market just exploded with this narrative that Google's Ironwood had successfully dethroned NVIDIA. Where did all that intense media hype come from?
It was really a perfect storm of technological proof points and some very strategic marketing from Google. It all followed the successful global rollout of TPU v7 in November 2025. And it really felt like a validation of Google's 10-year, multi-billion-dollar bet on building their own custom silicon.
And the first, and probably the loudest signal, was the announcement around their new model, Gemini 3.
Precisely. Google went out of their way to publicly emphasize that their flagship frontier model, Gemini 3, was trained and served exclusively on their own internal TPU infrastructure. They said they relied 0% on NVIDIA.
That's a direct shot.
It was a direct, unmistakable challenge to NVIDIA's claim as the universal engine for AI. It was Google saying, we don't need you anymore.
And then came the reports of competitors, other hyperscalers, starting to explore using Google's hardware. That must have sent a powerful signal to investors.
It sent a shockwave. We saw credible reports that hyperscalers like Meta, which has its own ASIC program, were actively evaluating or even planning deployments using Google's chips, specifically for their large-scale inference workloads.
Why them?
Because the soundbite was just too compelling. The repeatable phrase you saw everywhere was that Ironwood was 4 times faster at half the cost.
Now, that's a very specific claim.
It was, and it was often attributed to specific, standardized, high-volume inference tasks like language processing, but it was a powerful marketing message.
So you have this combination of Google's vertical integration, the chip, the software stack with JAX and XLA, the cloud infrastructure. It made their whole AI hypercomputer offering seem like this unassailable fortress.
It did, but let's apply the reality check that's necessary for this deep dive. The dethroning narrative is largely a clickbait headline. It's designed to generate market volatility and clicks.
Those are the real story.
NVIDIA still dominates. They have over 90% of the market share. CUDA is still the default standard for almost everyone. The more accurate, more nuanced conclusion from all the sources is that Ironwood has successfully established itself as a legitimate second pillar of the AI hardware ecosystem.
So it's not a takeover, it's just real competition for the first time.
It's intense, legitimate competition, and that's a very different thing from a dethroning.
Okay, let's strip away the marketing spin then and just look at the raw specs side by side per chip. Because when you do that, the gap is incredibly tight.
It's amazing how close they are. If you look at raw processing capability, let's say in terms of FP8 compute, Blackwell is slightly ahead. It clocks in around 9 petaflops of sparse processing.
Compared to Ironwood.
Compared to Ironwood's 4.6 petaflops of dense capacity. Though, as we said, Ironwood's dedicated sparse cores help make up for that density gap in those MOE architectures.
And memory.
Memory is a virtual draw. They both have 192 gigabytes of HBM3E. Bandwidth is also very comparable. Blackwell's at about 8 terabytes per second, and Ironwood is at 7.37.
So if the specs on paper are that close, the real difference must lie in the architectural philosophy. It sounds like they're engineered to win two completely different types of races.
That is precisely it. Blackwell's strength is its flexibility and its maximum performance peak. It absolutely dominates in peak throughput, especially when developers can leverage that groundbreaking FP4 support.
And its general-purpose nature, combined with the CUDA ecosystem.
Makes it the undisputed winner for mixed research workloads, for scientific computing, and for generalized AI training. For a researcher, that flexibility is almost always more important than a marginal efficiency gain on one specific task.
Okay, so that's Blackwell. What is Ironwood's undisputed strength? Where does it win?
Ironwood wins the TCO and scale game, total cost of ownership. Its architecture, with those optical interconnects, allows for that extreme cluster scale, forming those 9,216 chip pods.
And its energy efficiency is superior.
Far superior, measured in watts per token. So for a company like Google or one of their major partners like Anthropic, who is committed to the TPU stack, the total cost of ownership is the only factor that matters. For massive, standardized inference serving, our sources suggest Ironwood can reduce TCO by anywhere from 30% to as much as 52%.
Okay, now hold on. A TCO number that's 30 to 52% lower. That is a staggering operational advantage. So here's the friction I see. If the advantage is that massive, why isn't every single major company jumping ship from NVIDIA tomorrow?
That's the critical business question, and it comes right back to the CUDA ecosystem. That TCO saving only materializes if the cost of migrating your entire software stack, all your models, all your engineering talent, is less than the savings you get.
So it's a switching cost problem.
It's a huge switching cost problem. For a brand new startup writing code from scratch, maybe the math works out. But for a major enterprise with a decade's worth of PyTorch and CUDA-based models in production, the cost of rewriting everything and retraining their staff could wipe out that TCO advantage for years.
So NVIDIA's moat isn't just technology. It's measured in millions of lines of existing code and the collective expertise of hundreds of thousands of developers all over the world.
Exactly. Google has the better, cheaper engine for their specific high-volume tasks. But NVIDIA has the better, more universal highway that everyone already knows how to drive on.
And that leads directly into the biggest constraint on Ironwood, doesn't it? The production paradox. Availability.
This is the key business reality. Google, at its heart, is a cloud company. It is not a component seller. Google does not sell TPUs standalone. You can't just go buy an Ironwood chip.
They're only available through Google Cloud as part of their AI hypercomputer platform.
That's it. And this is a radically different business model from NVIDIA, which is a global hardware supplier. NVIDIA sells Blackwell hardware to everyone, every major cloud provider, AWS, Azure, even Google Cloud itself, as well as directly to OEMs, national labs, enterprise clients.
That supply model ensures NVIDIA's market omnipresence.
It does. Ironwood, by contrast, is primarily what we'd call an internal fortress and a strategic cloud differentiator for Google. Its constraints mean its incredible technological edge is locked inside the Google Cloud ecosystem.
So it can't really erode NVIDIA's unit market share significantly.
Unless Google Cloud can persuade a massive number of customers that the TCO advantage is so huge that it's worth being locked into the Google stack for their high-volume inference needs.
So let me see if I can summarize the choice. If I'm a new AI company and I need maximum flexibility to deploy my models across AWS, Azure, and maybe my own private data center, I have to choose Blackwell and CUDA.
It's the only practical choice.
But if I am Google, or a huge partner like Anthropic whose needs align perfectly with the TPU's specialization for massive scale and cost optimization, Ironwood is the only rational choice.
Exactly. The chip war is less about which chip is universally better, and it's much more about which architectural philosophy best serves a specific business model.
And this rivalry, Ironwood versus Blackwell, as intense as it is, it's really just the most visible part of a much larger market trend.
Which is the rapid fragmentation of the AI hardware market. It signals the definite end of the GPU monopoly. Every single major cloud provider has realized they cannot afford to be strategically dependent on a single vendor for their most important operational infrastructure.
This is the huge hyperscaler ASIC explosion we're seeing. It's internal competition driven by the need to optimize for their own specific internal workloads and, crucially, to bring down their procurement costs.
You see it everywhere. AWS, the biggest cloud provider, is deeply invested in their own custom silicon. They have Trainium for training and Inferentia for inference. These are cost-optimized, predictable chips designed to service AWS's absolutely colossal and diverse customer base.
And Microsoft is right there with them.
Microsoft has followed suit with their Mayo chip, which is engineered specifically to handle the enormous scale and the very specialized needs of their Azure cloud, and, of course, their key partners at OpenAI.
And then there's Meta, which has its own unique set of problems to solve.
Meta's MTIA platform is tailored primarily for their gargantuan recommendation engines. Those are the algorithms that drive Facebook and Instagram. And those workloads require super high throughput for extremely sparse data, which is a totally different optimization problem than training an LLM.
And you even see it with companies like Tesla and their Dojo supercomputer.
Dojo is a radical custom architecture designed for one thing and one thing only: their internal self-driving compute.
So what's the implication for the listener, for the AI builder out there?
It's incredibly positive. More competition means lower costs across the board for everyone. And more than that, it empowers developers to mix and match their hardware.
So you could use Blackwell for your early research and training where you need that flexibility.
And then once your model is finalized, you can swap it out to run on a custom ASIC like Inferentia or a TPU for your high-volume, cost-sensitive inference. You get to optimize your entire pipeline from end to end.
And the innovation isn't just confined to the multi-billion-dollar hyperscalers. The sources show this really vibrant ecosystem of specialized startups that are pushing the boundaries of physics and architecture in fascinating ways.
I find these startups almost more compelling than the giants. They're willing to take the kinds of risks that a huge company just can't. Take a company like Cerebra's, for example, with their wafer scale engine.
This is the one that's a single chip the size of a dinner plate.
Or a pizza box, as some sources describe it. They literally take the entire circular silicon wafer and make it the chip, the whole thing. This completely eliminates the need for chip-to-chip interconnects, which maximizes on-chip communication speed and memory access. It's a radical design for massive training runs.
And then you have a company like Grok, which is focused on predictability and deterministic computation with what they call language processing units, or LPUs.
Grok's LPU architecture is all about deterministic, ultra-low latency performance, mainly for inference. In real-time conversational AI, predictability is everything.
You don't want your chatbot to suddenly lag.
Exactly. A user expects the AI to respond quickly and consistently without sudden latency spikes. Traditional GPUs, which are juggling lots of different asynchronous tasks, can sometimes struggle with that. Grok's design ensures that near instantaneous, predictable response time.
We also see Tenstorrent, which is led by the chip legend Jim Keller. They're pursuing a high-risk, high-reward approach using open-source architectures like RISC-V combined with specialized AI acceleration.
And we can't forget the growing influence of the Chinese competitors. Companies like Cambricon, Biren, and Alibaba's Hangwang chip, they're all aggressively pushing their own domestic ASICs.
Well, the market trend is just undeniable.
It's unmistakable. ASICs are specializing. They're creating these deep niches where the general-purpose GPU is gradually being elbowed out. The entire hardware landscape is rapidly rapidly becoming multipolar, with each chip optimized for a specific high-value workload.
And this specialization is now spilling out of the data center and into our pockets, into the hands of the consumer. These dedicated mobile accelerators are transforming flagship smartphones into really powerful, on-device AI supercomputers. This is the shift to edge AI.
The performance improvements are just staggering. Your phone today is capable of running a localized LLM with better performance than a supercomputer from 2012. And that's entirely thanks to specialized hardware called neural processing units, or NPUs.
Google's own Tensor chips, for example, in their Pixel phones. They include a mobile TPU core.
And that allows for things like real-time translation, complex photo editing like their Magic Eraser feature, and crucially, the on-device operation of their Gemini Nano LLM.
And Apple's doing the same thing.
Apple is deploying its custom neural engine across its entire silicon lineup. It's the backbone for features like Apple Intelligence. The current neural engines are capable of performing up to 18 TOPS, that's tera operations per second, and that power is dedicated solely to local processing.
In Qualcomm's Snapdragon chips.
Their Snapdragon NPUs are delivering even higher theoretical peaks, somewhere in the range of 10 to 45 TOPS. And that's supporting everything from advanced AR and VR to always-on biometric health monitoring.
So why is this edge AI revolution so critical for the user? Why does it matter that the processing is happening on my phone?
It solves three core problems. The first is latency. You get zero latency because the data doesn't have to leave your device, travel across the internet, ping a server miles away, and then come back.
The second must be cost.
No cloud cost, which saves the providers billions of dollars and enables them to offer these amazing services for free perpetually to the user. And the third, and maybe the most important, is privacy.
Right. Sensitive data stays on your device.
Your personal photos, your health metrics, your private conversations with the AI, it all stays local. It's processed by dedicated hardware that never shares the raw information with the cloud, and the data confirms this shift. By late 2025, over half of all flagship smartphones shipped with a dedicated, powerful AI accelerator. The most powerful AI is rapidly becoming the AI that lives in your pocket.
Okay, so we've established that the current battle between Ironwood and Blackwell is all about energy efficiency. But as we look out across the next decade, from 2025 to 2035, the sources we've looked at suggest this isn't just an economic optimization anymore. It's becoming an impending planetary crisis.
The data is really stark.
Yeah.
Data centers right now consume roughly 2 to 3% of all global electricity. That's already a huge number. But the industry forecasts suggest that without radical transformative shifts in computing architecture, that consumption could realistically hit 10% or more by 2035.
10% of all electricity on Earth.
Just for data centers, that scale of energy demand is completely unsustainable. It creates an existential challenge for the continued scaling of AI.
So the future race is explicitly not about raw FLPS anymore. That's over. It's about minimizing the energy footprint.
Companies will literally live or die based on their ability to minimize their watts per token and their joules per training step. This sustainability crisis is what is driving the most radical research into fundamentally new forms of compute.
And this push for sustainability and speed is moving research beyond traditional electron-based silicon into the realm of new physics. The first, and maybe the most compelling area, is optical AI chips, computing with light.
The concept of using light instead of electrons sounds like science fiction, I know, but the fundamental difference is pretty simple.
Okay, break it down for us.
When you push electrons through copper wires, you generate a massive amount of heat and energy loss due to resistance. That's why data centers need these gigantic, complex cooling systems. Photons, the particles of light, don't heat up in the same way, and they travel much, much faster.
So optical chips aim to replace the electronic components with light-based ones.
They aim to replace the massive matrix multipliers of a classical chip with things like light modulators and interferometers. You're literally doing math by interfering beams of light with each other.
And what are the potential gains from that?
The promise is enormous. We're talking about a potential 100 to 1,000 times improvement in energy efficiency compared to the electronic chips we have today. Alongside that, you get ultra-high bandwidth interconnects.
And who are the pioneers here?
Google Research, building on the optical interconnect work they did for their TPUs, is a major player. And there are also a number of startups like Lightmatter and Lightelligence that are making real progress.
But the sources also point out some pretty significant hurdles that are preventing this from being a widespread solution today.
The manufacturing complexity is immense. You have to build these new hybrid fabs that are capable of precision silicon manufacturing right alongside very sensitive photonics integration. It's incredibly difficult. And furthermore, most of the current optical designs rely on analog computation.
Which means it can be noisy.
It means there are precision limitations and noise interference issues that have to be solved before they can reliably handle high-precision training. However, for inference, which is repetitive, predictable, and can tolerate slightly lower precision optical chips, offer the most significant long-term leap in watts per token efficiency.
Okay, so the second radical departure from today's technology takes its cue directly from biology. Neuromorphic computing. Chips that are modeled to literally think like a human brain.
That's the goal. Traditional AI chips are inspired by the structure of neurons, but they still operate synchronously based on a central clock that ticks millions of times a second. Neuromorphic chips use something called spiking neural networks, or SNNs, and event-driven computation.
What does that mean, event-driven?
It means that instead of doing continuous calculations on every clock cycle, the artificial neurons on the chip only fire a spike of energy when a certain input threshold is hit, just like biological neurons. This dramatically reduces the amount of wasted computation.
And they handle memory differently as well, right?
Yeah, they do. They integrate synaptic memory directly alongside the processing units. This drastically reduces the most power-hungry step in modern computing, which is constantly going out to fetch data from external DRAM. The result is ultra-low power consumption, often measured in microwatts.
Microwatts, that's tiny.
It's tiny, and it makes them perfect for always-on edge devices. Intel's Loihi 2 chip is a key example here, and there's ongoing research at NVIDIA and IBM as well.
So what are these neuromorphic chips actually good at in the real world? Where would we use them?
They excel at sensing, perception, and real-time sensor fusion. Think of a robotic system where the input is highly sparse and time-dependent, like a camera stream or an array of tactile sensors on a robot's hand. Neuromorphic chips are incredibly efficient at handling those kinds of edge perception tasks.
So they're ideal for robotics, smart dust,
Yep.
tiny autonomous AI agents that have to operate for years without active cooling or be recharged. Okay, finally, let's address quantum-assisted AI. And I think it's critical we clarify the role here. Quantum computers are not going to replace classical chips like Blackwell or Ironwood.
That distinction is paramount. They will function as specialized coprocessors.
Right.
Quantum computers are brilliant at certain types of math problems that classical computers find impossibly hard, so they can be used to accelerate very specific tasks, particularly in optimization, which is essential for complex reinforcement learning, and in rapid sampling and search over enormous state spaces.
So we're not talking about a quantum LLM running on a qubit chip. We're talking about a hybrid approach.
Exactly. The sources we've seen are predicting things like hybrid quantum GPU training loops and quantum-assisted gradient descent by the early 2030s.
So what would that look like?
It would mean a GPU or a TPU handles the bulk of the standard matrix math, but the quantum coprocessor is periodically called upon to accelerate the most complex optimization steps in the training process. This could potentially reduce the training time for the most complex frontier tasks from months down to weeks. It's a very specialized tool for a specific class of problems, working in concert with the powerful classical architectures we've been discussing.
So all of this architectural diversity, the ASICs, the optical chips, the neuromorphic chips, it's all converging to create what our sources are calling the distributed intelligence fabric. We're moving toward this idea of a seamless AI agent that can follow you, moving across all your devices and locations effortlessly.
This is the edge cloud hybrid AI model. The AI model is no longer running in just one place. It's distributed across these massive cloud superclusters, powered by Ironwood and Blackwell.
And also on local hubs, like your home server or your autonomous car.
And right down to your personal edge devices, like your phone or your smart glasses.
In this distributed model, it seems like it solves the remaining big issues of latency, cost, and privacy all at once.
It does. Sensitive data, like biometric input from your watch or your private conversations with your AI assistant, will be processed locally. That's private inference running on specialized mobile NTUs or these emerging neuromorphic chips. That data never leaves your device.
Meanwhile, the heavy lifting, like training the huge multimodal world models and delivering that core foundational knowledge, is all handled by the cloud superclusters.
And the outcome for you, the user, is this truly seamless agent, a personal AI companion that knows your preferences, understands long-term context, and can move effortlessly from giving you directions on your smart glasses to summarizing a massive legal document on your laptop.
With zero perceptible latency, maximum privacy, and infinite scalability, because the compute happens wherever it's best performed.
That's the vision.
Okay, so to wrap up our look at the future, let's try and synthesize a forecast for the year 2035 based on all these market shifts and architectural decisions.
Let's do it. First, ASICs, like Google's TPU, AWS's Trainium, and Microsoft's Maya. They will come to dominate high-volume, predictable, large-scale inference and production workloads. Their total cost of ownership advantage for standardized tasks will just be insurmountable.
Next, GPUs. NVIDIA's Blackwell and its successors, like Rubin. They will retain their position as the general-purpose research engines, the foundational platform for general training, and the scientific computing backbone. And they'll be upheld by the enduring power and flexibility of the CUDA ecosystem.
Then, the new players, neuromorphic and optical chips. They will come to define ultra-efficient and specialized compute. They'll establish dominance in edge intelligence and specialized inference where power consumption is the absolute highest priority. They'll eventually replace some of the current generation NPUs in embedded and mobile devices.
And critically, the primary business trend will be vertical integration. The major cloud providers, Google, AWS, Microsoft, will mostly run their own chips for the vast majority of their internal workloads.
The overall shift is away from the single GPU backbone that defined the last decade to a much more resilient, multi-vendor, multi-architecture landscape. The same force of specialization that birthed the TPU is now fragmenting the entire compute market.
So this deep dive has really shown us that the scaling of intelligence demands the specialization of hardware. The evolution from the general CPU to the parallel GPU and now to the hyper-specialized ASIC, that's an irreversible trend. The future of AI is going to be defined by architectural diversity and, above all else, by energy efficiency.
And the rivalry between Ironwood and Blackwell is the perfect case study for this. Ironwood is optimized for maximum scale and cost savings in standardized inference, and that creates an economic fortress for Google Cloud. Blackwell, secured by its CUDA moat, remains the champion of flexibility research and peak throughput for generalized workloads. And this intense, healthy competition, it drives down the cost of compute and accelerates innovation for every single person building AI applications today.
We're entering an era where the largest, most significant breakthroughs in AI are being written not just in new lines of code, but in the physical design of the chips themselves. So here's the provocative thought we want to leave you with. We are shifting from an era of raw, centralized power to one of localized, efficient intelligence. In the year 2035, which unseen AI agent will you rely on most? Will it be the powerful hyperscale agent powered by the cost-optimized Ironwood architecture deep inside a data center somewhere? Or will it be the nimble, private, neuromorphic-inspired agent that's built right into your smart glasses?
The way you experience the world, your reality, in the next 10 years will be entirely defined by the outcome of the Silicon Wars we have just analyzed.
Thank you for joining us for the Deep Dive.